Okay, well, so today what I'm going to do is I'm going to look and do a short introduction to the concept of the mole and what that means and how you use it. And the thing to remember about a mole is that it's exactly the same as something like a dozen. We all know what a dozen is. It's 12, right? 12 things. And so you could have a dozen donuts, a dozen eggs, a dozen puzzle pieces, all right? Anything, a dozen. It's a really simple concept. And all that means is you've got 12 donuts. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A dozen donuts. And those could be a dozen eggs too, right? Because I don't draw very well. A dozen puzzle pieces, a dozen pencils, right? It doesn't matter what it is. We know what the concept of a dozen is. And that's a number we've been using pretty much all our lives. We know it's 12. And if I tell you a dozen plus 2, you would know that would be 14 because that's 12 plus 2, right? And if I told you it was 2 dozen, you would know that was 2 times 12 equals 24, right? And so how do you use that concept? Well, suppose I told you that one egg weighed 4 ounces. And I would say, well, how much does a dozen eggs weigh? And you would go, so an egg is 4 ounces per egg. And then there are 12 eggs per dozen, right? And see, what's going to happen here is egg is going to cancel there. And then I just multiply this and I get 4 times 12. And then the units on that are ounces per dozen. And so this is just 48 ounces per dozen. And that's how you work with a dozen. So if I told you a pencil was 2 ounces, how much does two dozen pencils weigh? Well, this is 2 ounces per pencil. 2 dozen is 24 times 24 pencils. And this is 2 times, and this is also 48 ounces, right? So there should be no great mystery as to what a dozen is and how you would work it to figure out how much something weighs. And conversely, if I told you that a dozen cartons of milk weighed 144 ounces, how much does each carton of milk weigh? Well, okay, there are a dozen carton of milk, so that means there's 12 cartons. We know those 12 cartons weighs 144 ounces. So how much does each carton weigh? 144 divided by 12. And this is ounces. And this is cartons. And we're going to come out with 12 ounces per carton. Right? Pretty simple. There's no magic in that. And there's nothing magical about the concept of a dozen. And it all should be pretty simple to understand, or straightforward to understand, I think. And so that's how a dozen works, right? And a mole is exactly like that. It's just a mole is an impossibly huge. So a mole, instead of being equal to 12, is equal to 6.022, and then some other numbers that we're not going to worry about, times 10 to the 23rd, right? Which is 6,022, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 23. Right. So that's how big a mole is. It is whatever that number is, 6.022 times 10 to the 23rd. Let's see, there's billions, trillions, quadrillions, quintillions, septillions, I don't even know what that number is, but it's huge, right? This is a lot. And if we were trying to count that, that's probably more seconds than in the age of the universe. So we wouldn't really even be able to make sense of that number. At least not in our lifetime. We wouldn't be able to calculate it in our lifetime. Better. Okay. So that's what a mole is. And that's all it is. And you could just think of it as a glorified dozen if you want to. But that's all it is. It's just a number. And it just tells you how many of these things we have. And we use the mole because atoms are impossibly light. They have very little mass. And so we have to have this huge number here. So we talk about counting atoms, we have enough to actually measure. And this number comes out to be this because of some intricacies of how people originally defined the metric system in grams and kilograms way back when. And it just so happens that this becomes what's called Avogadro's number, 6.022 times 10 to the 23rd. But it's just a number. There's nothing complicated about it. And we could call it a chemist's dozen if we want to, and it would be the same thing. I mean, it would mean the same thing. And so when we use a mole, it just tells us how many atoms there are or how many molecules there are of something, right? So we could talk about 1 mole of nitrogen atoms, N, right? And 1 mole of nitrogen atoms is going to weigh about 14 grams, right? So we would say that nitrogen atomic mass is 14 grams per mole. What does that mean? It means if you took 6.022 times 10 to the 23rd nitrogen atoms, little n atoms with 7 protons, 7 neutrons, and 7 electrons, and we weighed those 6.022 times 10 to the 23rd atoms, right? They would weigh 14 grams, right? 14 grams per mole, that's all it means. And if I told you I had 28 grams of nitrogen atoms, how many moles of nitrogen atoms would that be? Well, 28 grams divided by 14 grams per mole, right, is going to equal 2 moles. How did I do that, right? Okay, well, it's the same thing we did before with dozens, sort of, only we haven't worked it in a little bit different units here. And so let's work it the other way, forgetting about this for a minute. And let's think about how much so we know that a mole is equal to 6.022 times 10 to the 23rd items, whatever it is we've got, right? And then we know that the atomic mass of something is the mass of 1 mole of those atoms. Right? Okay, and then we could talk about the molecular mass is mass of 1 mole of those molecules. So how many atoms are in 1 mole of oxygen? Well, there is 6.022 times 10 to the 23rd. How many molecules there are in there in 1 mole of water, H2O? Well, there are 6.022 times 10 to the 23rd molecules, atoms. Okay. How many molecules are there in 1 mole
of oxygen gas, which is O2? Well, there are 6.022 times 10 to the 23rd molecules, right? But each molecule is 2 atoms, right? That's what that little 2 means. So how many moles of oxygen atoms are there in 1 mole of oxygen molecules? Well, there is 2 times 6.022 times 10 to the 23rd atoms of O in 1 mole of O2, right? So that's how you think about this in terms of quantities. And remember, mole is just a shorthand for this. That's all it is. It's just a number, right? So it's just a shorthand. So how do we use that in some calculations? Well, say I wanted to know how much 1.5 moles of sodium metal weighed. Sodium metal, Na, okay? That's the symbol for sodium. Well, the atomic mass of sodium is about 23 grams per mole, right? And then I'm going to have 1.5 moles of it. So 1.5 moles, right? And so I just multiply that, and these are going to cancel, and I'm going to get 23 times 1.5 grams, which is equal to 34.5 grams, I believe, doing the math in my head. Okay. So all I did was I just multiplied the atomic mass by the number of moles, and then I get the number of mass, right? So you could turn that around and say, well, let's suppose I have 11.5 grams of sodium. How many moles is that? Right. Well, in the book, they tell you that you just divide the weight by the atomic mass, right? So the atomic mass is 23 grams per mole. So Na is 23 grams per mole, right? And then they set the calculation up a little weird in the book. So if we're just going to divide the mass, we would do 11.5 grams divided by 23 grams per mole, right? And that's going to equal 11.5 divided by 23. And then these units work out to be grams times mole over grams, right? And I'll go through what's happening here, but these are going to cancel. And this then just becomes 11.5 divided by 23 turns out to be 0.5 moles. So all I did was divide this by this, okay? Now what's going on with the units? Well, if you remember back to Math 98 and looking at rational expressions, whenever I have A over B over C, right, for a rational expression, that this is equal to A times C over B, right? So basically this part here in the denominator inverts and you multiply it like this, okay? So this then equals A times C divided by B, okay? That's just how rational expressions work, right? And so what's going on with the units where we have grams over grams per mole is units are working sort of like these things, and this becomes grams times moles over gram, right? See here, this would be B, this would be C, and this would be A, and so here's A, and here's C, and here's B, right? And then these two things are just going to cancel, and we're left with moles, right? So that's what's going on there.
right? And then in the book, they do this particular one a little way. They do this calculation and they write it in a weird way, which is a little bit confusing. They write this as equal to 11.5 grams times 1/23 moles per gram, right? So what they did was they wrote this as a multiplication by 1 over the inverse, because they're using the thing that says that A over B is equal to A times 1 over B. Right? So, and you can show that this is true by showing that we could write this as, I don't know, you could think of this as A over 1 times 1 over B, and then you're going to get A times 1 over B times 1. So those cancel and get A over B, right? Anyway, this is what's going on in the way they've done. There it is. Get all that gobbledygook out of there. So this is how they did this in the book, is they wrote it in this format here. So you've got this, and then this, and then they come out with moles. Right? But they're just multiplied by the inverse. So it looks a little weird, but when they say in the text that you divide the mass by the molecular weight, or I'm sorry, molecular mass, that's what it would look like, but they wrote it like this, which is the same thing mathematically. So that's what's going on with those examples. And I hope that that makes that a little clearer how that's working for you. And hopefully you'll get some use out of that. Anyway, I will talk to you later.